Hi there. I'm Felix Clock, and I'm here to tell you about an awesome new technology called RR. It's going to change the way that you look at debuggers. RR stands for record and replay. So what RR does is it records all the source of non-determinism as your program runs, and then lets you re-execute your program, replaying those events, those non-deterministic events, at the exact same points in time at the instruction level. So and to give you some idea of how awesome this technology is, I used to be somebody who used my Mac to do development. I switched entirely to doing as much development as possible on Linux just so I could leverage this tool as much as possible. A little bit about myself. So I've been at Amazon since October of 2020. I'm part of the new Rust platform team there, where we are working to help Rust deliver on its promise of efficient code that is memory safe and has no data races, and also to make Rust productivity high, to make Rust development a joyful experience for all of our customers, the customers of our team, who are the Rust developers themselves. We all Rust developers are the customers of our team. Um, I've been a compiler hacker for over 2 decades, with a number of years of garbage collector development mixed in there. And I can tell you, I wish I'd had a tool like R available to me when I was doing GC work, because it would have made solving a number of bugs a lot simpler. And I've been a Rustation since 2013. There's been a number of RFCs I've been involved with in that work. But this talk is about debuggers. And I have had a love-hate relationship with debuggers for about 25 years. And I think the tension there, the reason why it's a love-hate relationship, is because the tension between the use of the debugger. Sometimes it seems like an irreplaceable tool. There's some problems in my mind that I felt like I could have solved without the ability to use a debugger to inspect things. But some of the other times, it feels like you're just flailing around in a debugger. It's a crutch as you're trying to, understand a program, or worse, it's distracting you from even seeing or understanding what the program's behavior is. So one of my favorite quotes along these lines is from a lecturer I had at university, where they said, "A debugger is no substitute for thinking," which is true. It's a very good point. But there is a counterpoint to this, which is that sometimes you have to stop thinking and look. There's a bunch of problems that you cannot resolve just by thinking about it in your head. You have to make observations about actual behavior and act on those observations. And a debugger is a wonderful tool for making observations. Okay, so that's, maybe a little bit of the love, but what about the hate? Let me try to illustrate the hate with a toy program. So this is a little program that we're going to actually see running, and it's a little clock, a terminal clock that's going to spit out text at a certain frequency. So let's go ahead and see it run. This is a Rust program, so normally you type cargo run to run it, but I'm going to run the program directly in the binary by just invoking it directly with the initial frequency of 2. So now this clock is going to spit out a line every 2 seconds. It gives a time that this is run, and it gives the something that's increasing over time, little bar thing. I can hit characters to change the frequency. I change the frequency to 1, then to 3, and you can see that the frequency which the lines are output changes accordingly every 1 second, every 3 seconds, so on, back to every 1 second now. So that's this program. Okay, now let me show you what it's like to try to explore the behavior of this program in a debugger. If we were in the 1970s, we would use maybe GDB to explore the behavior of this program. So I would type GDB, and then I would give it the program name. And then once GDB fired up on that program, I'd tell it, okay, start running the program with this input, the initial frequency of 2, let's say. And now the program is run. We stopped at a certain point in the program. We can list to see a bit of the source code. We can use the next command to say run until the next statement. You could hit enter, repeat the last command, and that's a way of sort of stepping through your program, doing next, next, next. I hit a function call here with a callback. So in order to get to there, I want to set a breakpoint inside the callback and then continue to that point. So I set break continue for break 22 and then continue, and it stops at line 22. And then you can look at the program source again. This is a way to work, but it's pretty miserable. It's really painful to have to constantly remind yourself about context in this manner by relisting the source code. So one answer to that problem, say, yeah, you should use a different front end, or you should use a different debugger. But let me look at GDB itself for a little bit first. So there's an option here to make things life a little bit better. Control X A is a command you can emit to GDB while you're sitting there running it. So I'm just spelling this out here in text, but I hit Control X A. Whoa! Now we're in the 1980s. Look at that. So now we actually see our source code. We get direct feedback about what line we're on while we're in that source code. We can still use the command next and hit enter, enter, enter to, go down through step through the program the same way as before. But now, we're at least to see some direct context of where we are. And we sometimes get output to the screen, so we have to hit Control L to refresh the screen to stop because it was a little bit corrupted by that. But that's not the real problem. The real problem is this. I realize something when I get to this point in the program as a user, and I say, oh shoot, I meant to look at the value of timestamp that it had before it was overwritten on line 36. If you look on line 36, that value of timestamp is overwritten with the value of now, which means I've lost that state, and maybe I wanted to see it for some reason. This is the heart of what the problem with using debuggers is. Spelunking through the caves of your program with a typical debugger is not fun at all, because sometimes, as I just illustrated, you may want to inspect state that's been overwritten. And more generally, every time you make a step in a debugger, it's a one-way door. It's something where you've made that choice and now you've moved forward your program, and you've lost the ability to inspect things in terms of the context of where you were before. So mutations, or even making calls through dynamic dispatch where maybe you cared about where that call came from. You can go up the stack, but the point is there's things that happen where sometimes you would have preferred to actually go back and see what was the state before this thing happened. Um, okay, so one might say, okay, yeah, you're using the debugger wrong. You're just like playing around and doing next, next, next. What you should be doing is looking at your program, hypothesizing points of interest, and then setting breakpoints at those points of interest. And then when you hit those breakpoints, you inspect data. You step a little bit. You think. And that is a response to that, mode of operation. But this view overlooks one crucial step 4, which is that when you make a mistake, when you misstep, you curse, and then you restart your program from scratch. In other words, every debugger step is a one-way door. There's no getting around that. Okay, so a reasonable response to this is to say, yeah, well, this is why I use print line debugging. That's entirely true. Print line based debugging and more generally logs are useful. And one reason why they are useful is because you can visualize multiple points in time in a log output. Kernighan and Pike put this very nicely in practice of programming, where they point out that clicking over statements in a debugger actually takes longer than reading the output of a log. And it takes more time to step that way than it would just to add new print statements. And so the point here is this insight is unsurprising, especially if you're someone who knows that debugging steps are one-way doors, and thus you're going to agonize over each such step. Another way to look at this, to put it simply, is there's no such thing as whoops, I stepped too far when you're reading a transcript. There is whoops, my instrumentation was broken, but that's a separate problem. But what if? Let's revisit that whole question of whoops, I stepped too far, right? So let's talk about RR. So with RR, the way the mode of operation is, you have a program, you want to interact with it, you want to capture its behavior. So you do RR, you run the program again. And there's no GDB here. All we're doing right now is just running the program like normal. I hit 1 to get a new frequency, just like before, and I see a different frequency of output. And then I can hit another character. I think I hit 5 right now in my recording of this. So yeah, we get every 5 seconds now as the outputs. This is just the way we were interacting with it before. Nothing new here. Okay, and then you keep running it, and you're looking at things, and then maybe you notice something. You say, oh, there's something interesting. And so I don't know if you saw it, but I did. I'm gonna hit Control C now, and we'll talk about this in a little bit about what I just saw. So something interesting happened. Now I want to inspect it more carefully. So I do RR replay. I type RR replay, and what that does is it reruns the program, but it does it in GDB. So I'm now inside of GDB, and I want to set a breakpoint at the start of my code, and I say continue. And here we are at the start of the code, and we hit next. The same way we did before. Next, 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 hitting enter to repeat the last command. We can hit Control X8 to enter TUI mode, just like before. And it's the same deal as we had before. We can see we're at that crossbeam scope call. We can set a breakpoint at line 22. We can say next now to just say move forward and stop at the breakpoint. And it's the same mode of operation that we had when we were working with GDB before, right? All we're doing is using next to step through the code and getting some feedback about where we happen to be. Nothing different there, except that we're doing a replay where we don't have to worry about producing user input. We're getting the user input from the replay that happened before. But mostly it's the same. Here's where it goes different. Here's the different part of the story. So if I'm at some point in the program, I can now type reverse next. I can do reverse next, and now it goes backwards. You see that? I do reverse next again, and it goes backwards again. And we keep working our way back up, backwards through the flow of time. We can do next and go forwards. And we can just keep going back and forth as we like to explore the code. So we can see we're now at this point in the code I mentioned earlier where there was that new line call. So if I set a breakpoint on that new line call and continue to that point, now I'm sitting here at that new line call, and if you remember from before, my issue with at this point in the program code was that I wanted to know about some previous piece of state. Well, I can do reverse next, and then hit enter to keep reverse nexting to go backwards to where I was up above, work my way backwards ever so slowly, and then I'm at the point where timestamp is overwritten. Okay, if I print the timestamp value right here, I can print it out using GDB technology, and look, I get this big gobbledygook of Rust structure. That's okay. I can use field dereference operations to see the specific piece of state I'm interested in, the number of seconds, let's say. So now I see 77,236 seconds. I can say, okay, print now, the number of seconds on now, the same way, and I see 77,238 seconds. I hit next, and I go through that statement. I can now print the timestamp here. You can see it's been updated to the value that it now held. I can do reverse next to go backwards, and I can print the value there, and it has the old value. I'm not reverse next and next are not just changing the program counter. It's actually going back in time. It's updating the whole state of the memory of the system to reflect the way it was at that point in time, and that is amazing. So that was my sort of spiel about splunking through code with RR. Next, I want to sort of give you the overall picture for the talk as a whole. So I'm first going to talk about why RR is different from the things that have come before it. Then I'm going to talk about the practicalities of using RR, especially if you're on a virtual machine or if it's on a cloud desktop machine, for example, in AWS EC2. And then I want to give a demo of solving a real problem using RR. So how does RR differentiate itself? Well, I think the crucial way to look at this is that reversible debugging, as I just showed you, is pretty cool, but record and replay is useful. There's plenty of cool technologies in the world that do not provide utility. RR does both. It's the brainchild of Robert O'Callaghan from when he was at Mozilla Research, and the motivation for it was intermittent test failures. If you have some failure in your software that occurs 1 every 1,000 runs, what happens in practice is your continuous integration is doing thousands of runs, and it will report the failures. But the engineers are not doing thousands of runs, so they see the failures being reported, and they try to reproduce it, and they can't. They don't see it in their local system. And furthermore, when they investigate and look at the commit that's being blamed by the CI, they say this commit versus this test that failed, they'll say these two things are clearly not related at all, and they'll just ignore the failure. They'll say we should move forward with the commit. This is a huge cost. There's a lot of engineering time wasted on such fruitless investigations. And furthermore, there's this question of how do you even deal with this? What did you do in response? Do you disable these so-called flaky tests? They represent real bugs. Just because the software that you're running has non-determinism doesn't mean that you get to ignore it. And these are real bugs that might need to be investigated and resolved. So here's an old idea, is to record the source of non-determinism and then replay those events back. It's an old idea. It has had many predecessors, but nothing has had serious customer adoption. And at the heart of why is basically either they've been too high overhead. When I say high overhead, I mean like hundreds of times slower or thousands of times slower than what running the actual binary would be, or they move the goalpost. They change what the goal is and say, oh, the output, we're going to make the output roughly the same, but we're not going to guarantee the execution was actually the same. Or in some cases, you have hardware solutions where the efficiency is actually pretty high, but it's super costly to deploy hardware-based solutions to this. So RR is a totally different story. Things work off the shelf with RR. No changes to hardware, and in fact, no changes to your OS. So it works with x86-64, and it works with off-the-shelf Linux. No kernel modifications, and you don't even have to load up a kernel module. It's also low overhead. We're talking like 20 to 50% overhead in running times, which is amazing compared to hundreds or thousands of times of overhead. It works by monitoring a single process, but it'll include the spawn threads of that process. So if the process spawns off multiple threads, that's fine. They'll get included in the recording. And it doesn't rely on any code instrumentation, because basically the engineers of RR said it's too hard to even implement that in the first place. And also it's too high overhead. So that means it works great in the use case of a just-in-time compiled code in like Firefox, where you're emitting code on the fly that would otherwise have to be instrumented on the fly. And it works on real programs. Like I just said, it's used on Firefox, and I use it on the Rust compiler itself. It works on real programs, not just toys. How does it work? Well, it leverages modern features of hardware and of Linux. We're talking modern in like within the last 10 years or so. So a Linux process has system call results and signals that are inputs. So they basically get these inputs into your deterministic CPU, and you can capture them. You can capture and intercept those events via ptrace and then respond to them accordingly. So R does that. Another issue is that you have shared memory access as a source of non-determinism. If you have two cores that both access the same piece of memory and do things with it, then that's a source of non-determinism. R deals with that by limiting the process to a single core. So what this means is that if you have multiple threads, which you can do, it just means that they'll be scheduled onto a single core at a time, and so it's not truly parallel. This is a known limitation of RR. It's just a fact of life for this technology. How does it work then beyond that? Well, it uses hardware performance counters as its notion of time. So it figures out based on the performance counters when the events, these asynchronous, these non-deterministic events actually happened. And then for the replay, it sets interrupts based on those event counts and says deliver the same event at the exact same time. And this is practically zero cost because it's just using performance counters that are already built into the processors that you have in your desktop. And beyond that, there's a lot of other details. It uses BPF, it uses descheduling events. There's all these details in Robert O'Callaghan's talk. But I think the crucial takeaway is that there's a lot of different features being used here that are not meant for this purpose. And they just happen to combine them in a way that just happens to work by accident. Okay, so the practicalities of using this thing. Well, it just works. On Intel x86-64 it works, and also on 32-bit Intel it just works. On AMD it works as well. On Ryzen, AMD Ryzen, you do have to disable a certain model-specific register, but R will detect if that register is enabled, and then tell you if you do it, try to run R in that context, it'll give you a little printout saying run this script, and it'll disable the register. So it's really easy to make it work under AMD as well. And ARM Linux is under development. If you're not on Linux, sorry, it's not available there, and the R developers, it's not that's not a market they're interested in trying to target. So sorry. Like I said, I switched to Linux for this thing. So how do I know if it's going to work on my context of my virtual machine or my cloud desktop? Well, you can just grep. You can say run dmessage and grep for the message, corresponding message, and either you'll get a yay message, as in like something that says the performance events are compatible, or you'll get boo. You'll get something that says nope, it's software events only, and that's no good. In particular, if you're trying to do something on a cloud desktop under, like, for example, AWS EC2, well, you can use a whole number of instances that'll work. Basically, you need a dedicated CPU socket. And I've tested this. This demo I'm giving of this program that I'm running is actually on an AWS desktop. So this does work in the cloud. Okay, and how do I use this thing? Well, first, I've already sort of showed you the basics of GDB in terms of setting breakpoints and doing continue and whatnot. But the other thing I want to mention is that watch points. I haven't shown you watch points yet, and they're very important. They're an important idea. Basically, if you want to observe when a part of memory is overwritten by some, in the future, you can set a watch point and give it an expression for that piece of memory describing it. So you can say like, a variable, a local variable, or you can say even something that's heap allocated, just give it the description in C of how to get to it, and then it sets a watch point, and the processor will break as soon as it sees a write to that location. What about RR? It's the same set of commands. It's the exact same set of commands, except that they just add some extra ones. They add these reverse next things I illustrated. But these other commands, these other variants are super interesting as well. For example, reverse continue just means go backwards in reverse until you hit a breakpoint. Reverse finish on the GB side means finish running to the end of this function and basically run until you hit the caller, and then resume from where the caller is, but stop right there. Reverse finish means go backwards in reverse, which means go to the call site where this function was called, which is a very awesome thing to be able to do, to just keep jumping backwards and inspect again and again as you're running. But also crucially, watch points still work here, which is amazing. Okay, so let's actually look at debugging a real problem with RR. So the deal here is that if I want to I'm going to do a replay again, and I'm going to see here. Oh, right. So the -a flag for RR is a way to say basically I want to see the replay without running GDB. So it's a way to basically see the replay again, and that's interesting. Um, but another detail, another flag you can give to RR that's a little bit more interesting is that you can pass the -M flag, and what that will do is it'll annotate the output with a notion of how much time has passed according to RR's notion of time. So if I do -A-M here, what will happen is it'll do a replay, and then it will include the event count. It'll include the process ID and then the event number of events that have happened according to R's notion of time. And if you look at this output now, I want to notice something. In fact, there is a bug, and you may not have noticed it yet, but it's been there the entire time since I took this trace. That was the interesting thing I pointed out when I said there's something interesting that happened. If you look, there's a line count that's happening in the output. Lines, it's line 0, 1, 2, 3, 4. If you scroll down, line 12, after that it says line 14. We missed something. Something went wrong there. We missed a line. Or the counter's not being updated correctly. So the question is, how can we use RR to debug this problem? Well, I will point out now that in particular, if you look, event 569 is where we observe the erroneous output, right? That's because that was the annotation that we see there on the prefix of that line. So we know something about this error. We know this error can be observed by looking at event 569. Okay, so what I'm going to do now is I'm going to use Emacs Good mode to debug this, and I'm going to do it via a wrapper script. So we have a wrapper script called Rust GDB for invoking GDB on Rust code, and I'm going to make yet another wrapper script around Rust GDB. And what it's going to do, Rust GDB uses an environment variable to figure out what GDB executable to run. So I'm going to tell it to run RR as its version of GDB and to start debugging from event 569. So here's my wrapper script that I'm using to invoke Rust GDB, which will then invoke RR via this level of indirection here. So I'm going to start up Emacs, and I'm going to tell it, okay, when I start up Emacs, I'm going to use Emacs Good mode, because this is just an easier way for me to interact with this system in terms of the debugging here. But it's a lot like 2E mode. It's not, you won't see that many differences in my opinion. Um, so I'm going to tell it to run GDB using the wrapper script I just made. We see the output that I was describing earlier. We see that we're in GDB now. We started in the middle of the program execution because it started at that event count that I mentioned earlier. So we can look at the output and see, yes, we saw lines 0 through 12, and then it started up GDB right at the point before we emitted line 14. So you can see that in the output that we have here. We can see that start up GDB, and then the program is halted waiting for us to do something. We can say continue, and when we say continue, it'll spit out the remaining lines, 14, 15, 16. Okay, that doesn't actually help us that much, but we can rerun. We can rerun and give it an event number, and when we do that, it starts from that event number. Okay, so now we started from, emitting lines 0 through 14. Um, so at this point, I realized when I was working on this and capturing this demo that, gee, this output is not as useful as it could be because it doesn't include the event numbers, right? You're seeing the lines of output from the original program, but not the event numbers according to RR. So what I decided to do was go into that wrapper script again. And this time, in addition to telling it to play RR with this event number, I'm also going to use the capital M flag to include the output about the event numbers in the standard output that it generates. So now when I run good GDB and give it that wrapper script, I get this output where it spits out this information here. And now if we look, we see the output of the lines that are emitted, and we see the prefix of the events for each line. Okay. And again, if we look at this, we can say run from line 5. We can look and say, yep, line 5, event 569 was the one we care about. So we can say continue and finish running the program from there. I can say run 569, which means start debugging from line 569. And we see all the output again, and we're sitting here. We're sitting right at the point where we observed the erroneous output. We are sitting at that point where we're about to spit out that line 14. Okay, what can we do here? We can do up. We can say go up the stack trace in GDB. We're right now in the guts of RR, but if we go up beyond that and move our way up, we'll eventually get to the Rust standard library. We go up some more. I'm just saying enter, enter, enter to repeat up, to keep moving up through the standard library until eventually I'm going to get to our actual code right here in time passages. Here we are. This is the spot where we saw line 14 being emitted to the screen. All it's doing is a print line, right? This is where we observe the line that was incorrect because there's a buffer internally, and this is where that buffer gets flushed. We add on the number of bars and the flush to the screen. So it's not where the erroneous output was created, and it's not even where the piece of state that we care about was corrupted, but it is where we see it, observe it as a reader seeing the output. So where did this information get corrupted? Well, we could trace around to try to find that, but I'll tell you right up front, this lines variable is, I know what that's the thing that's being corrupted because I know the code well enough to know lines is wrong. The question is, why is lines wrong? Where was lines been corrupted? And RR gives you the tools you need to figure this out. You can set a watch point on the lines variable, which is something you can do in GDB, that's normal, and you can say continue in GDB, and that will just keep running the program, and it'll stop as soon as this thing got overwritten, which is what happens here. We're somewhere in the guts of Rust to where that atomic variable got overwritten with a value, and we see in the GDB output, the gut output, that it got changed from 15 to 16. Okay, but what I care about isn't when it got changed from 15 to 16. What I care about is when it was corrupted in the past. I can do reverse continue, go backwards. And now I see where it got changed to 15, from 14 to 15. I can do reverse continue again, and I get to see where it changed from 13 to 14. And this is amazing. It's something where I'm going back in time based on when those data got updated. So I can go up the stack and I can see, here's the place where it got updated with 14. And you look at this and you're like, yes, this is a new line call, but it's right after a print statement. You know what? In terms of the invariance of the program, this makes sense. This is fine. But if I do reverse continue again, because this isn't the point where it got corrupted, if I do reverse continue again, I'll see the point where it got updated to 13. And now if I go up the stack, I see, aha, this is where lines gets updated. And if you look, there's a call to print line right above it. But it's been commented out. There's the bug. There's the bug. It's somewhere that this state got corrupted because someone commented out the print line statement, but forgot to comment out this update to lines. And that is the bug right there. And we found it super fast in a very directed fashion by combining watch points with replay-based debugging. Okay, so the crucial point here I want to get is that you can run RR without the debugger, if that might be useful to you, and you can hard code, when you're using the debugger, you can hard code memory addresses. Because it's all deterministic replay, your hash tables are going to be laid out the same way, and your memory addresses that you get from the memory allocator are going to be the same, which means you can do tricks that were not available with a normal debugger if things are non-deterministic. So that's amazing. And then you can use things in terms of these event numbers to actually jump directly to the point in time that you care about, which is I was illustrating by rerunning the program and inspecting certain events. But more generally, you can change your whole mindset about debugging because the one-way door of a debugger step has been replaced with a two-way door with RR. And this means the debugger can start being a useful exploratory tool for you to use in practice. So with that, I'll stop there and just say thank you for listening. And I hope you all go out and if you aren't already using Linux, you go ahead and install it and then you go and download RR and try it yourself. All right, thanks a lot.